Hey guys, we are in Unit 4 here, BC4, and this is going to be all about parametric and polar equations. So far we've kept it in terms of x and y, and we call that like rectangular coordinate field, okay, because it's like a rectangle, I guess. But so we've been in x and y and everything, but now we're going to have a parameter introduced. So it's like a third variable, and then we're going to go to polar, which is just beautiful. But essential questions, if you want to look through those. We're going to just kind of start with some pre-calculus on parametric. So in our parametric here, we can see we're now going to have this three variables going on. Okay, so instead of just having the x and y, we're going to have like x in terms of another variable, and it's almost always t because of time. And then we'll also have y of t. And you can actually put this into your calculator. If you go into your mode in your calculator and get parametric, and then go look at your y equals button, and you're going to see it's going to say like x sub 1 and y sub 1, and then like x sub 2, y sub 2. So this would be like the first set of parametric equations because you're going to need both x and y. So it breaks down things more for you. It's kind of giving you the horizontal movement with the x and the vertical movement with the y. So it's giving you more information, and it's telling you how that movement occurs with respect to t, the time. So whenever we're sketching parametric equations, we always want to have arrows because that's like the newer piece is that we have that orientation. So let's go ahead and start. And here I can see if I look at this x, with that t, the t has to be greater than or equal to 0. So I know that my x is going to have to also be greater than or equal to 0. And here, with that t, I can see that as I plug in all the different values of what y could be, or what t could be, y could be anything. But if I'm only looking at greater than or equal to 0 here, then my y is going to end up being less than or equal to 3. Okay? So let's see how that looks. As I plug in a 0 to this guy, square root of 0 is 0. And here, 3 minus 0 is 3. So 0, 2, 3. So this was at t equals 0. So now let's go plug in a 1. Square root of 1, 1. 3 minus 1 is 2. So now I'm at 1, 2. So this was at t equals 1. Now when I plug in this is like some square root of 2, which is approximately like 1.4142-ish, okay? So here I'm just going to have to approximate, but then when I plug in my 2, I get out 1. So at 1.4-ish, I'm at 1. And that's at t equals 2. At 3, I have radical 3 and 0. So radical 3 is still less than 2, and I'm at 0. And then at 4, I have 2 and negative 1. So here I can see the movement is going in this direction. So I drew a lot of arrows. You don't have to have that many, but you do need to show the direction. That's what a parameter is all about. So go ahead and have fun. Go put this into like your x1 and your y1 in your calculator and see what happens. All right, eliminating the parameter. A lot of times you want to go from parametric form here, and we want to get it into rectangular form. So all you need to do is solve one of these guys, go solve for t. So I can either solve for t in this one, or I could solve for t in this one. And if I solve for t over here, I'm going to have plus or minus the square root of y. So we don't want to have two equations going on. So I'm going to go over to the x and solve for t. So that means I need to e both sides and then divide by 2. And now I'm going to go plug that into the t here. And so this would be the rectangular form, and these were the parametric form. So they are exactly the same. Sometimes the domain and range can be a little bit different. So let's check out this domain. So I'm going to go ahead and graph that in terms of t and x. So the ln, it's going to look like this. So here I can see my t is greater than or equal to 0, but my range here, the x, is all real numbers. And then let's go look at this graph. T and the y, and it's a parabola looking like this. So on this one, my t can be all real numbers, but my y here is greater than or equal to 0. And even if I limit the t for what I see before and only look at the greater than or equal to 0, my y is still greater than or equal to 0. So I know that I wanted my domain to be all real numbers, and my range is y is greater than or equal to 0. And check this out. This e to the x actually has the exact same domain and range, so I'm not limiting anything. So kind of nice. Well, actually I am limiting. Look, this cannot be equal to 0 here because it's a horizontal asymptote. So I don't even need that guy there. These are nice. They're just kind of some equations. If you want to memorize them, great, but I'm going to show you how you can convert when you have x and y with the cosines and sines or secants and tans. We're going to use, when we convert these, the Pythagorean identities. So cosine squared plus sine squared is 1, and 1 plus tan squared is secant squared. So we're going to be using these, or you can just have those guys memorized. That's kind of up to you. And then just really a lot of review from all of the conic sections with ellipsis and hyperbolas, parabolas. So do as much review as you kind of need to on this page and looking over and see if you had any questions. Okay, but all of that page is pre-calculus. So if not, maybe you'll kind of catch on as we are writing these. So I want to sketch, oops, I don't know what that's doing. Sorry, cancel, go away. Okay, I want to sketch the curve represented by these two functions. So when I see those, instead of me going back to what I showed you at the original, I like to use this Pythagorean identity. So secant squared is x squared here, and tan squared would be y squared. So I'm just kind of squaring both sides. And then using substitution. So when we want to find what's going on here, I'm going to have this head and equal to 1. So y squared minus x, nope, other way, equal 1. So I got to bring the y over. So x squared minus y squared equals 1. And you can put it over just the 1 here, so it makes life a little bit easier. But when you have the minus, I don't know if that's going to, but when we have the minus, we want to have a, that's a hyperbola. Okay, so we're going to draw the hyperbola. And here I can see on the x-axis, I go out 1 in both directions from my center. And here it's centered at 0, 0, because I'm not plus or minusing anything within the square. So my center is right here. And then the x I go out 1 and 1, and in the y I also go out 1 and 1. So then I draw my box, and then I draw my asymptotes. They go through the edges of the box and through the center. And then here, since the y is minus, I know that it's not on the y-axis, it's the x is the positive, so my parabola, or not, my hyperbola is going to be on the x-axis for those vertices. It would look like that. Super cool. And you can go and put this into your graphing calculator, into that x1, y1, and you're going to see the same thing. So it's pretty awesome that we can go back and forth between the parametric and the rectangular here. Okay, so let's look at this one. So here I see sines and cosines, so I know that I need to get into sine squared, or not, t here, plus cosine squared equals 1. So I'm going to square my x, and I'm going to square my y. And then I just want sine squared, so I'm going to divide the 9 over, and I just want cosine squared, so I'm going to divide the 4 over as I go substitute it. So this is y squared over 9 plus x squared over 4 equals 1. So this plus lets me know I have an ellipse, and I know it's not a circle because these are not the same values. If they were the same values, it'd be a circle. This is an ellipse. So in the y direction, remember 9 is 3 squared and 4 is 2 squared. In the y direction, I go out 3, and in the x direction, I go out 2. And then I was from the center, and the center here was at 0, 0 again. Sorry, I should have said that. We go out from the center. And then I can draw my ellipse. So finding a set of parametric equations, this is actually kind of fun. You can find an infinite amount. You kind of just say, hey, let x equal anything in terms of t. So what if it's just t? Then what's y? Y would be 2 over t minus 1. So pick something else for x that you want to plug in here. So maybe like t plus 1. So then y would equal 2 over t plus 1 minus 1 would just be t. I mean, we could do this like crazy. We could pick lots of things for x. So we could say let x equal t squared. That's the third one I'm looking at. So then that'd be 2 over t squared minus 1. So there is an infinite amount of possibilities here. Now, what could be different is the domain and range could be different. So that's the only thing. All right, so all of that so far would have been some pre-calculus, and so now we're actually going to get into a calculus piece of this parametric stuff. Okay, so horizontal and vertical movement, we already kind of talked. The x is talking about horizontal movement, and the y is talking about the vertical movement. And so if I kind of look at just the derivative of the x's, if I'm positive, then I'm going to the right. And if I'm negative at that derivative, then I'm going to the left. And looking here, when the derivative of y is positive, I'm going up. When the derivative of y is negative, I am going down. So it's just breaking it up into more pieces. And remember, like rise over run is still slope. So my slope here is still just y prime over x prime, that change in y over change of x. Okay, that's that instantaneous change over the instantaneous change here. So pretty easy just to get the slope. We take the derivative, evaluate it at the number of the y, and we take the derivative of x and evaluate it at the number and divide. Okay, so here's an object. It says it's moving in the xy plane so that at any time, this is what x of t is, and this is what y of t is. What is the rate of change, aka slope, of the y with respect, there we go, to x when t equals 3. So it's just saying, what's the slope when t is 3? So I need to take my x and take the derivative there. Squared minus 6t, and I need to take my y and take the derivative of that. That's my chain rule. And those, that's nice, those kind of cancel. And then I also need to plug in my 3. So x prime of 3, 927 minus 9, and plugging in my 3 here. 9 plus, that's 5. So 3/5. So now let's go ahead and do my entire slope when t is 3 is that y over that x part. And feel free to reduce it if you'd like. Guess we kind of have to if we're going to match on the multiple choice, and we get B. So one more thing, we really want to know this, okay? The particle at rest, well, back in rectangular, I knew the particle was at rest when the velocity was 0. So we learned that in calculus 1. But now that we are in parametric, we have to have both of the equations, the x and the y prime, being 0 simultaneously. So they both have to equal 0 to be at rest. So this gives me an x and y, and it says when's the particle at rest. So I need to take the derivatives and find when each of those are equal to 0. Oh, I should take out a 3 there. So over here it would be 0 and 2. 2 minus t. Over here it is just a 2. So the only place where they are both equal to 0 is at t equals 2. But wait, it says which of the following points. So I know it's going to happen when t is 2, but now it's actually wanting me to go a step farther and get the point. So to get the original point here, I'm going to have to go and plug 2 into my x and into my y. 2, 4, 12. So at -4, 12. Okay, let's go do an AP example. For t greater than or equal to 0, particle is moving along a curve so that here's my x of t, y of t at time equals 2. The position is 1, 5. Okay, so when t equals 2, I know I have an x of 1 and a y of 5. And then they also give me the derivatives. So they did not give me the original equations. They just gave me the derivatives. Okay. So this one says, let's go see. Usually when I have a derivative and a point, I bet one of those is going to ask me to do the fundamental theorem of calculus to find, like, add another point. That's my guess if I was to look back at that AP example. But we're just going to focus on A here. Is the horizontal movement to the left or the right at t equals 2. So horizontal movement is just wanting me to focus on the x piece, horizontal. So I'm going to look at that derivative when t equals 2 of the x piece. So here, when I plug in a 2, I get the square root of 4 over e squared, which is 2 over e squared. And I know that this is positive over positive, so this is positive. So therefore, we are moving to the right. Then it also has a second piece here, and it says, go find the slope at 2. Well, we've already done the x prime, basically, of 2. That's that same thing. So I need to find the derivative of y at 2. We're going to find dy dt when t equals 2. So that would be sine squared of 2. So now my entire slope, dy dx, when t is 2, is the y over dx. And you do not have to reduce this. If it was me on that test, I would leave it. But for those of you who want to flip it up because it's just driving you crazy to have that double fraction, feel free. This was a calculator active, even though we didn't even need it. So calculator, if you did do that, you could get one of these two answers if you truncated or rounded. But for the love of me, okay, try not to simplify. And here is a recall of the fundamental theorem of calculus, what I was just mentioning earlier. Usually when we know a derivative and we know like one value, like t equals a number already, and then we know like one of the outputs, then we're going to use this fundamental theorem of calculus. So this was like a part B of this. It says, hey, here I've got a point and I've got a derivative and it wants to know what am I going to be at 4. So we have to do these two separate for the x and for the y. So here, let's do the x first. So I'm going to put my derivative with respect to t, and I know what happens at t equals 2. I want to find out what happens at t equals 4, and this is where we set up already the full equation. So this is x of 4, that's what we're looking at, minus x of 2, which we know was 1. So the x value when the time is 2 is 1. So then I actually put this into my calculator, into that math 9, and get my answer. And then I can add 1 over, and I will have the x. And there you go. So let's go do the y. Actually, see if you guys can do the y on your own. Go see if you get 5.563. Okay, that'll help you. And then you can leave it just banked like this, or you can write it in the coordinate form. It's up to you. Either way, this or this doesn't matter. But make sure you can get this on your own. If not, let me know and I'll help you out. Okay, so that's the end of day 1.